Okay, for our day 2 notes, we're going to continue working with polygons and look at our angle sums in the polygons. Before we start, just a reminder, you guys did learn that in a triangle, the sum of the angles inside the triangle will always equal 180 degrees. So we'll be using that today to discover some new things. Couple definitions here. A convex polygon is a polygon where the diagonals are all on the inside. So it's a polygon where the diagonals are inside. So that means from every vertex, if I draw across diagonally to another vertex, they are always inside the polygon. Okay, and a concave is a polygon where our diagonals would be on the outside. And it could be one or more. Or outside. So let me show you an example. Here, this diagonal, so that's going from one vertex to another, that would be inside. However, if I try to do here, to go all the way across to that other vertex, I'd be going outside of that shape. Same thing here. It's outside of that polygon. Okay, and so that's what we call concave. You can kind of see also it goes in. So let's just identify a couple here. This one here would be concave. This one is also concave. Whoops. And if you just want to double check, every diagonal that I can draw is on the inside. That's convex. Let's see. Okay, redo that. Okay, this one here would be convex. Oh, see, I'm all messed up here. Okay, redo. Okay, starting here. We're going to identify each polygon as convex or concave. So this one, if I were to draw all the diagonals, they would fall inside. And so this is what we say, convex. This one here, if I try to draw a diagonal, it's going to go outside the polygon. Same thing here. So this would be concave. Again here, it goes in. If I try to draw a diagonal, it would be on the outside, concave. And then this last one, convex. So moving on, we're going to look at the sum, back to our sum of interior angles. And we're going to do this chart together and discover the sum of the interior angles of a polygon, how we can always find it based on the number of sides that our polygon has. So if we start with the triangle, and like I mentioned up above before, we know that every triangle, when I add all 3 angles, I'm always going to have 180 degrees. Okay, so a triangle has 3 sides. There is only one region. I can't divide it into any more because if I try to draw a diagonal, there's no other vertex to connect to other than the sides. So we say it has one region and the sum of the angles are 180 degrees. Okay, this next one, and I'm going to divide each polygon, and notice by drawing all possible diagonals only from one vertex. So that's kind of important there. So I'm going to pick just one vertex. So let's say I start there. And if I connect, the only diagonal I can draw is to that other vertex. The other ones are the sides there. Now, notice by drawing that diagonal, it divides it up into 2 regions, and each region is another triangle. So that's 180 degrees total of all the angles in that section. And then this is another section with all the angles would add up to 180. So for any quadrilateral, has 4 sides, I can divide it up into 2 triangular regions. And because we have 2 sections that are both 180, that gives me a total of 360 degrees. So in any quadrilateral, we would have the sum of angles equals 360 degrees. Okay, a pentagon. Again, I'm going to pick just one. Let's say I pick that one. And I'm going to draw all the possible diagonals just from this one vertex. So there's one. And there's another one. All right, and our pentagon has 5 sides. There are 3 regions. And each region, again, if I were to add up the angles within that region, would have a total of 180 degrees. So we have 3 regions with 180. That would give us a total angle degree of 540. All right, a hexagon. Same thing, let's take a look. I'm going to pick one of any vertex, and I'm going to draw diagonals to as many of the vertex that I can there. So that hexagon has 6 sides, and we ended up dividing it into 4 regions. 180, 180, 180, 180. That's going to give us a total of 720 degrees. So by filling out this chart, I can look at some patterns here and see for any polygon, is there a formula that we can use so that we could figure out the sum of the measures of the angles in any polygon. So a pattern that I notice as I'm going the number of sides, every time I divide it by that diagonal, that is going down by 2. So notice we had number of sides was 3. The number of regions was 1. Here I had 4 sides, I get 2 regions. So if I have n, let's just say, as my polygon, whatever number of sides it is, I can figure out the number of regions by taking the number of sides and subtracting 2. All right, and then moving on to look at the pattern here. The number of regions, we were always just taking the number of regions, and I know I had to multiply that by 180. So like here, there were 4 regions. I did 180, 180, 180, 180. So 180 times 4. So we're multiplying the number of regions by 180. So if I were to set that up as an expression, I could show that I'm doing 180 times my number of regions, my n minus 2. And there we have it. So for our sum of interior angles in a polygon, our formula is 180 times n minus 2. And that n is your number of sides. All right, so even if we had a polygon with 10 sides, I could do 10 minus 2 and then multiply it by 180. Okay, another chart to fill out here, regular polygons and their interior angles. So similar, we're going to look at the measure of just each angle, one interior angle. So for a triangle, we know it has 3 sides. The sum of all the measures of angles is 180. And if that's the case, 180 divided by 3, we know each angle has to be 60 degrees. Okay, for a quadrilateral, 4 sides. And we know it's 90, 90, 90, 90. That's a total of 360 degrees. Okay, and we also have this information from up above here. We're just kind of using what we did there. However, one of the interior angles would be 90 degrees. Okay, our pentagon has 5 sides, and that had a total of 540. So if I add up all the angles in that pentagon, it's going to total 540. The measure of each angle, though, however, would be, I would have to take this sum of the measure, the total, and divide it by 5. And that's going to give us 108. Okay, for our hexagon, 6 sides, and the total sum of measures of all the angles was 720. Each angle, if I were to divide that, because there are 6 of them, and they're all congruent, would give me 120. Okay, so again, what we were doing was using. Okay, so down here now where it says n-gon, this means for any polygon given the number of sides, we would be able to figure out the measure of one of the interior angles. So let's use a variable. We'll say n here. So if it was n. And our sum of measures of angles, we had that in our table up above. And we said that was 180 multiplied by the number of sides minus 2. And so what we're doing here is whatever the sum of the total amount of angles is, we were dividing by the number of sides because that was the same amount of angles. And that gives us one interior angle. So to find the measure of one interior angle, we were taking our total amount, our sum of the total, and dividing it by however many angles there were, the number of sides. And so to write that out, I can say it's 180 multiplied by the number of sides minus 2. And all of that was then divided by the number of sides. All right, and so if we just want to summarize it and write it down here, so we'll have it 180 multiplied by the number of sides minus 2, because that was from our pattern up above. But then if we want just one of the angles, we have to divide it by the number of sides. Okay, and then lastly, we're going to take a look at the exterior angles in polygons. And we have an exterior angle sum that is the same. So let's just take a look. We're going to measure each exterior angle using a protractor. So you're going to need your protractor out, and then we're going to add up those angles to take a look. All right, so with your protractor, if you measure this exterior angle here, you should have come up with 120 degrees. This angle, if you put your protractor here, would also be 120 degrees. And this exterior angle would also be 120 degrees. So that is an equilateral triangle there. They all have the same exterior angle. All of our interior angles, just to label if you want, would be 60. I know the sum of the inside angles is 180. However, our exterior angles, and so notice when you extend it for the exterior angle, you're just kind of going around and 120, 120, and 120. So that would give us a total of 360 degrees. All right, and then same thing on this quadrilateral. If you take your protractor, this measured angle should be 90. This one would also be 90 degrees, 90 degrees, and 90 degrees. So double check those with your protractor. And again, if we were to go around, the sum of those, adding them all up, would give me 360 degrees. And in fact, if I add any of the exterior angles of a polygon, when I go around, it will always be 360. So we can write this definition out here. The sum of exterior angles is always 360 degrees. Okay, that's it for standard 17.